Good morning, good afternoon, good evening. It is my pleasure to present the WGFF activities in this seminar. Currently, the WGFF chair is Dr. Bodo Mikan from PGB. Unfortunately, due to the private reasons today, he cannot join the seminar. So I'm the vice chair as a representative to present our WGFF activities. Currently, in the WGFF families, we have officially 20 members. They come from 4 RMOs. There's one members from AfriMet. It is from South Africa, NIST, and there's 4 members from the APMP area, Chris, NIM, NMIJ, and NMIA, and there are 11 members from the Euromet areas, from BEV, GAM, CMI, Mentas, IPQ, LNE, RIM, PTB, RES, 2, England, and VSL. And there are additional 4 members from the CCM area, from the Mexico, CNAM, and from the Brazil NMI Institute, and NIST from America, and NRC from Canada. From these pictures, you can see the distributions for the 20 official members for the WGFF working group. We also checked the available CMCs released in the website of the KCDB 2.0. Currently, there are over 500 CMCs released related to the fluid flow areas. The CMCs coming from the 59 institutes. Currently, the scope for the WGFF is related to the flow and related quantities. It is including the liquid flow, such as water, hydrocarbon liquids, and the low temperature liquid. And another is the gas flow, including the air, nitrogen, natural gas. And another topic is the liquid volume, from the microliter to thousands of liters. The last is the speed of fluid, including the air speed and the water speed. So within the scope of the WGFF, currently we have 6 key comparisons regularly, including the K1 for the water, the K2 for the hydrocarbon liquid and the water, and the K3 is for the air speed, K4 is for the liquid volume, K5 for the high pressure gas flow, and the K6 for the gas flow. And according to the requirement of the CCM and the CIPM, currently we have 2 gas documents released in the BIPM website. The first is the CMC uncertainty and the calibration report uncertainties. For this document, it is the guide on the uncertainty to ensure consistent approach for CMC entrance as well as at calibration report. This document was released in 2013. Another document is for the CMC review protocols. This document is guide on the review for the intra and inter-MO for new or modified CMCs to ensure consistent approach and efficiency work. In this document, in fact, according to the different area, we give very specified requirement for the CMC evidence. So this work is to help all the reviewers to get to do these reviews very efficiently. In fact, with the release of the KCDB 2.0, in fact, we are working on the revision of this review protocol. And this work a little bit delayed due to the pandemic, because this work already started before the pandemic. We have some very detailed discussions in person, but during the pandemic, this work was a little bit delayed. Last year, we have the hybrid meetings in our group. So this revision work will be finished soon. We hope the revision for this protocol will be released this year. And for the WGFF, the comparison is very important topic for us. And for the fluid flow comparisons, the transfer meter, the transfer standard uncertainty is very important. I will explain more later. So in order to give very proper evaluations for the transfer standard, we have very good reference from two important papers. One from the Dr. John Wright. This paper was released in 2016 for the transfer standard uncertainty can cause inconclusive laboratory comparisons. And another from the PTP colleagues from the content gave some related to the explanatory power of degrees of equivalence in the presence of the random instabilities of the common measurement. These two papers are very important for us to make the proper evaluations for the transfer meters, in fact. As I said before, I want to explain more why the transfer meters and uncertainty evaluations are so important for us. You can see here, when we make the comparisons for weight, in generally, for mass, in generally, the weight is used as a transfer meters. In our understanding for this kind of comparisons, it is the direct comparisons of quantities. Because during these comparisons, the comparison was conducted in very well controlled environment, and there's no any movement for moving component for the weight. So the transfer standards relatively very stable. But for us, you can see this typical gas flow facilities. You can see the facilities located in relatively big space. For the meters, the meter and the test, the transfer meters is here. And it is kind of turbine meters. It is generally used for the gas or the water fluid comparisons. For these comparisons, in fact, the flow rate is determined by the flow facilities, and we cannot achieve the exactly same flow rate. In fact, the exact flow rate is determined the conditions for these flow facilities. And due to the big space, in fact, the environment is too difficult to control very well. Not like in the comparisons for the mass, the temperature control maybe the temperature can be controlled minus plus 0.1 degree, something like that. But for the fluid flow comparisons, especially for the high pressure gas flow facilities, the temperature may be only controlled plus minus 2 degrees C or plus minus 1 degree C, something like that. And so, in fact, this many components for the flow meters. So, in fact, the final result, it is the complex result. It is kind of performance of the complete sensors result. And all the sensors have the drift. So that's the reason why the transformators evaluation is so important for us. In fact, according to our available knowledge for our work, in the future, our work will be focused on 3 parts. The first is to finish the CMC review guide as soon as possible. As I said before, this work is a little bit delayed because we want to, how to say, because there's a big change, big change for the KCDB website, and there's sorry, there's still some new requirement for these new guidelines. But anyway, we hope the new the revision guidelines will be released this year. And another important part for the WGFF is we hope we can develop the new method for the KCRV evaluation method. I will explain more in the next page. We have started some work for this topic. And another topic, important topic for us, currently for all the key comparisons in the fluid flow field, we typically use a classic hypothesis method to make the evaluation for the key comparisons. Recently, we started the work to make the Bayes hypothesis method for the key comparisons testing evaluations. Especially currently, the key file is going on. We will try our first time to make the Bayes hypothesis method to make this key file final evaluations. This is examples. We want to show you why the determination of the KCRV as a function is important for us. This is comparisons we organized last 2 years, and these comparisons for the high pressure gas comparisons. You can see here there's some parameters. The comparisons cover the different pressures from the 0.8 millipascal to 8.5 millipascal. The range is relatively wide, and the working fluid, including the air and the natural gas. So you can see here the point that the final result is not exact. We cannot find the exactly same result for different participants. So in these comparisons, according to the principle of the transformators, we developed these functions to make the curve fit like this, the orange curve like here. And for this curve fit, in fact, the most important thing is to find the method how to evaluate the parameters. So recent years, we try to develop some method to evaluate the parameters, and we developed the methods to evaluate the deviations and certainty like this. So with the curve fit family, we can calculate the EN values for individual comparison result. So finally, we can evaluate these comparisons. For the layer zones and the stakeholders part, in fact, currently for each RMOs, they all have the relatively TC is related to our working scope. So we organize the regular communications for all the IMOs, so we can discuss what they want WGFF work, something like that. And for other stakeholders, in fact, for INVICO TC9 is related to our scopes. And for this TC9, in fact, every 3 or 6 years, we also cooperate with TC9 to organize the International Flow Field Conference to communicate with all the colleagues in the flow field. We also have with close relationship with ISO TC such as 48 and 30s. And also, we have a close relationship with the legal metrology OIM TC8 and another accreditation organizations in the fluid flow field. Last, I want to show you our technology trend and the challenges. In fact, the further development of CMCs and related WGF work will reflect the challenge in meter technologies. As we know, currently, the carbon issue is a big issue all over the world, and the fluid flow is very important parameters to use to evaluate how much cost and how much emissions, something like that. So recent years in the fluid flow field, we are working a special focus on the decarbonization of energy supplies. Our research covered extended to the hydrocarbon from the productions, distributions, and the consumptions, and also extended to the synthetic biofuels and their usage. And for the CO2 part, we also start some NMS also start the work for the CCUS areas. And the other topic is balancing in transport networks and the leak quantifications for the methane, hydrogen, CO2s, including flyer measurement. And another topic for us is to extend the application fields and the sensor technologies, including the microflow, organ-on-chip, dynamic flows, multi-phase flows, waters, meter diagnostics, and sensor networks, and so on. That's all. Thank you. Thanks you for your attention. If there are any comments or suggestions, you can contact with Dr. Nita or me directly. Thank you.
Hello or good evening. This is Yoshitaka Fujita from NMIJ, Japan. So I'd like to introduce the activities of WGDV. This is an extraction from classification of service category relevant to WGDV. WGDV has 3 kinds of measurement quantities: density, refractive index, and viscosity. And in the KCDB, you can search the 237 entries of CMCs on density. And in density, there are 2 classifications of solid and liquid. And in density of solid, density and volume of artifacts such as silicon sphere and stainless steel weight are measured by hydrostatic weighing method. In liquids, measuring devices are oscillation type density meter and hydrometer. And In addition to these two devices, hydrostatic weighing method are also used in density of liquid. And the viscosity has 399 entries of CMCs. And these three classifications are for capillary viscometry. And two quantities of kinematic viscosity and dynamic viscosity are included in these classifications. And I think that this classification of reference liquid is one of the features of this WG. And as for the membership, chair is me, Yoshitaka Fujita, NMIJ, chairing viscosity, and vice chair, Luis Omar Becerra, Senam, Mexico, chairing density. But Luis Omar has recently sent us his intention of resigning vice chair, so we have to search next candidate in the near future. And presently, there are 26 NMIs, DI, BIPM, 6 RMO TCM chairs. And other than these members, as observers, approximately 10 NMIs have been participated in the WG meeting. And WGDB is a merger of WG density and WG viscosity in 2014. And the WG meeting held in the week of CCM meeting at the BIPM. And for this WG, it's difficult to hold a meeting at the conference or occasions or other occasions because there are almost no conferences together in one places for all the members of density and viscosity. So in density, we have many kinds of key comparisons depending on classifications of service category, such as solid, liquid, and measuring devices. So for the purpose of introducing outlines of comparisons, example of traceability system on density standard are shown. And density of silicon sphere is determined based on this defining constants, defining constants of SI, Planck constant, and speed of light in vacuum using interferometric method and mass measurement. And based on that primary standard, density of solid, such as several artifacts, are determined. And based on densities of those artifacts, services of these calibrations, such as density of reference liquids, hydrometers, oscillation type density meters, has been provided to the density users. And these are comparisons of density. CCM DK1, density measurements of silicon sphere being piloted by PTP and 11 participants, measurement in progress. And DK2, liquid density, pilot is not yet decided, and planning under consideration, and sharing activities for sample preparation by collaborating group, and also sharing cost among participants were suggested in the discussion of last WG meeting. And CCM DK3, density measurements of stainless steel weights being piloted by NMIJ, 15 participants, and protocol in progress. And CCM DK4, hydrometer calibrations, planning is awaited to start. And CCM DK5, density measurement by oscillating type density meter being piloted by BEV, 70 participants, and measurement completed. And lastly, pilot study of surface tension. And this was proposed as new field in last WG meeting. And about 7 NMIs are interested. Similar project has been implemented in the preceding Euramet project. So initiating planning by some NMIs of this project is expected. And this shows a comparison of refractive index of liquid. CCM DK6 being piloted by NMIJ. 10 NMIs, including a few NMIs in CCPR and DI are interested, and questionnaire in progress. And also showing standard liquids. It is to be distributed to participants, covering certain range of refractive index with several kind of liquids. And there are two methods for absolute measurement of refractive index of liquids. And one is a interferometric method. Refractive index is determined by measuring changes in the optical passes, optical path differences between sample and vacuum. And the other is minimum deviation angle method. The refractive index is determined by measuring minimum deviation angle of incident light and apex angle of prism. And this figure shows the total system of viscosity standard. Meteorological base is absolute value of water viscosity that is described in ISO. Based on this viscosity, instrumental constant of viscometers are successively calibrated up to the viscometer for high viscosity range, which is called as stepping up procedure. And by using these master viscometers, viscosity scale covers a wide range of viscosity that is more than 100,000 times the water viscosity. And 2 or 3 standard liquid with different viscosity level are distributed to the participant of key comparisons. And so far, 3 key comparisons have been already completed, and 2 key comparisons are underway. And CCM VK4 piloted by Senam, Mexico, and 12 participants. Draft B in progress, and this is almost completed. And CCM VK5 piloted by NIM, about 15 to 16 NMIs and DI are interested in participation. And the questionnaire will be prepared in the near future. And each key comparison has been carried out by alternating between wide viscosity range at moderate temperatures and moderate viscosities in the wide temperature range. And this is for guidance documents. As to the guidance documents, according to the CCM action plan, we presently have no document and has just started to work toward documentation about simplification and reduction of number of CMCs for viscosity. number of entries of viscosity is doubled by two quantities of kinematic viscosity and dynamic viscosity, and also tripled with the addition of reference liquids. So, kinematic viscosity is an essential quantity in capillary viscometry that is underpinned by key comparison. So, it was proposed in the last WG meeting that dynamic viscosity and reference liquid are merged into one entry of corresponding kinematic viscosity using comment column. And the next one is as the past result, WGDV contributed to establishment of the CIPM formula for the density of water in 2001, and then published guideline for the use of CIPM and IAPWS. IAPWS is the International Association for the Properties of Water and Steam. Also contributed to establish CIPM formula for density of air in 2008. As for liaison and stakeholders, in liaison, ISO TC48 SC4 regarding density hydrometer. At the request of this ISO committee, Vice Chair Luis Omar has participated in this committee and acted as liaison between the ISO and WGDV. As I mentioned before, in the past result, we had relationships with IAPWS on the guidelines for the use of CIPM and IAPWS formulas. And some members of WGDV are involved in RMO projects. For example, this Euramet project, one for density measurement and the other for viscosity measurement, have been reported in the WG meeting, in the last WG meeting. And as for stakeholders, industries of energy, alcohol, food, materials, refrigeration, and air conditioning, and manufacturers of density meters, refractometer, and viscometer, and reference material producers, and calibration and testing laboratories such as accredited laboratory and agency involved in taxation that is related to alcohol taxation using density measurement. And as for technology trends and challenges, realization of more accurate and reliable silicon density standard based on reduction of uncertainty in sphere volume measurement. And it is expected that this would reflect it in the result of key comparison on density measurement of silicon spheres and other variety of density measurements in the future. And supplying traceable refractive index standard liquids being ensured reliability by implementing key comparison CCM DK6 to meet the demand from food industry and agriculture. And supplying traceable surface tension reference for reliable measurement in science and industry. And application to interdisciplinary area based on accurate density measurement. One is seawater density measurement to predict global climate change. The other is PLOT properties and wide pressure and temperature ranges to meet the demand of improvement of heat pump system using alternative refrigerants to prevent global warming. And the realization of more accurate and reliable meteorological base for viscosity and standard viscometers with new technology other than classical glass capillary viscometry. And this is an interdisciplinary topic of density measurement for global environmental science. And global level circulation of ocean water affects global climate change due to its high heat capacity that is much larger than that of atmosphere. And in the study to understand the mechanism of global climate change, accurate density of seawater that is traceable to SI is required with uncertainty of less than 1 ppm. To achieve this subject, hydrostatic weighing system for seawater has been developed to increase in accuracy of standard seawater for calibration of oscillating tube densimeter used in the actual ocean observations. And this is a topic for realization of more reliable and accurate meteorological base for viscosity. Uncertainty of this meteorological base, the absolute value of water viscosity is 0.17%, that is described in ISO. But this uncertainty is not taken into account in the present viscosity standard. This is due to ambiguities of ISO value originating from a few results of previous absolute measurements. So new experimental results with modern measurement technology have been required to update this value. And to achieve this subject, absolute measurement system for viscosity determination at middle high viscosity by falling ball method has been developed. And based on this determined viscosity, viscosity of water will be determined by using stepping down procedure or capillary method with the uncertainty of less than 0.1%. That's all for my presentation. Thank you for your attention.
I'm Julia Scherschligt. I'm the recently became chair of the working group on pressure and vacuum. We were formed in 2014 through the merger of the working group on high pressure and the working group on low pressure, which of course is vacuum. And it was determined at the time of the merger that leadership must represent both aspects. So I am nominally a vacuum expert, and our vice chair, Dr. Hiroaki Kachikawa from NMIJ, is a pressure expert. We have 21 member institutes and 6 observer institutes representing all RMOs. And we have CMCs in pressure and vacuum that cover the range from nanopascal to hundreds of megapascal. Unlike some of the other working groups that we've heard from, we only concern ourselves with a single unit. So we're just worried about one thing, we're just worried about the Pascal, but we do have to worry about that unit over 18 decades. For context, 1 atmosphere is about 100 kilopascal, and it might be an interesting question to ask yourself, is this the distinction? Is this where we draw the line between what is pressure and what is vacuum? That sometimes is a nice way to think about it, but realistically, the distinction between pressure and vacuum is really more about the technology used to realize the unit and less about exactly where on this pressure range you're talking about. So it's more of a technological distinction and less about a numerical distinction. So in addition to these 18 decades of pressure, there are different types of pressure. We can talk about absolute, which is relative to a true zero, gauge pressure, which is relative to an atmosphere, differential pressure, which is of course relative to perhaps two sides of a membrane or some other physical barrier, and then different physical states. You can have a pressurized liquid or a pressurized gas. And then in addition to that, the working group also considers molar flow rate. So these are flows below about 10 to the minus 9 moles per second. And the reason this is part of our portfolio is because this is a subordinate topic to vacuum. Anyone who's worked on a vacuum system has likely been involved in leak checking. And in order to do leak checking, you use a helium leak detector that contains within it one of these calibrated leaks. And a lot of the technology used to do a calibration of one of these standards is the same as the technology that's used to do vacuum calibrations. And so it makes sense for us to also take care of that particular item within the working group. If you go to the website, you'll find a list of terms of reference, which nicely encapsulates the things that we work on. However, I find this a little bit hard to make sense of. It's a little bit too large. So I summarized it down to a few bullet points. These are our objectives as a working group. To define and organize and approve key and supplementary comparisons, to facilitate the submission and review of CMCs by establishing technical review criteria. I'll get into that a little bit later. To harmonize CMCs across the entire range and make sure that someone who comes to the KCRD, the database to look for CMCs across the NMIs is doing a fair comparison. Also to support innovation and improve techniques for realizing the Pascal. And then of course, to liaise with technical colleagues and stakeholders to ensure that our activities within the working group are aligned with their activities in the field so that as their needs evolve, our support evolves along with those needs so that in the future we continue to meet their needs. If you were to go online and look at our guidance documents, you would find the following. We have a document on the matter of choosing participants for key comparisons. The point of this is to minimize the number of participants while still making sure that all interested RMOs have representation. We also, of course, have all of the key comparisons are presented online, and we have a statement 2, which is regarding the need to orient CMC entries towards the unit under calibration. And this is because we cover across these 18 decades of pressure, there are a number of different types of gauge, types of technology. And if someone comes to the website to look for which NMI they might want to use to have something calibrated, they might want to search for that particular gauge. And we want to make that as easy for them as possible. This statement 3 is a relatively new one, and I'm not sure whether or not we have a final version of this on the website or not, but this was just recently completed within the past couple of years. It was developed by a task group that I was involved in. And what this thing does is it ensures that the uncertainty reported by the CMC includes an uncertainty from the unit under calibration. In other words, say we have two NMIs, NMI 1 and NMI 2. And NMI 1 believes that it is correct and appropriate to include the test unit uncertainty in their CMC, but NMI 2 does not. When they publish those CMCs, they're going to have vastly different uncertainty statements, despite perhaps being very similar in what they can actually deliver. And so someone coming to the website might think that their capabilities are rather different when in fact they're very much the same. In order to correct that discrepancy, we wanted to ensure that all NMIs are including the uncertainty of the unit under calibration and that they're doing it in a uniform way. So we just developed a list of best possible units under calibration for each type of pressure in each range, and a statement on the uncertainty of that best unit under calibration. Just going to flash these up so that you guys know what they look like. Say, for instance, I am interested in having a capacitance diaphragm gauge calibrated. I would be able to go and see that the CMC has this uncertainty included in it. So these are for gauge pressure, absolute pressure, gauge pressure in gas, differential pressure in gas, and then in the vacuum range. And then, of course, at the very end, we have those helium leak standards that I mentioned early on. One last guidance document to talk about is the one for reviewers of CMC entries. This is another recently completed document. And what this allows us to do is provide guidance for someone who's tasked with reviewing a CMC. Let's imagine that you've been given this task and you receive documentation and you don't know whether or not the documentation that you've received is adequate. And so you would go to this document and you would say, all right, I have received an application for a CMC, and I am going to determine using this document whether this is a high risk, a medium risk, or a low risk CMC. There are these charts in the document that will allow you to calculate the risk level based on the uncertainty claimed in the CMC relative to the uncertainties in this document. You make the determination of the risk level, and then once you have that, this example is for absolute pressure in gas medium up to 170 kPa. Let's imagine that you've established this particular CMC that you're meant to review is a medium risk level. Then you would go to this chart, and that tells you exactly what documentation you need to have in order to make that determination. And in our case of a medium risk level, you need to have a technical peer review or written overview of the measurement standard, along with key comparison or hybrid comparison. And then depending on the type of pressure that you have and the uncertainty level, these charts are available in the document covering all of the CMCs that we have. So that covers all of the guidance documents that we have on the website. The last thing before we get into the technology part is liaison and stakeholder activity. We're active in a number of technical committees, including IMECO TC16 for pressure and vacuum, the International Union of Vacuum Science Technique and Application, IUVSTA, a number of other vacuum societies, IVC, EVC, and AVS are all vacuum societies, along with the ISO Vacuum Technology Technical Committee. It's interesting to point out that most of these are oriented towards vacuum. There are not as many activities in pressure as there are in vacuum right now. And by and large, these stakeholders are primarily interested in, can we do something to shorten the traceability chain? And many, but not all of the stakeholders, of course, are also interested in the question of whether or not we can reduce mercury. The reason that's interesting is because historically, the primary pressure standard is the mercury manometer. The operational range of a mercury manometer is around an atmosphere. Pressures above and below can be traceable to manometry by potentially many successive comparisons. And so these liaison and stakeholder interactions lead us to ask the question, can we realize pressure at any or all ranges without reliance on manometry? So that is the guiding principle by which we ask, or by which we ask ourselves, oh, there go the dogs. What types of research projects we should look into. And it turns out that there are a number of ways to determine pressure that don't rely on successive calibrations traceable to a mercury manometer. And there are examples of this that span the pressure range from megapascal into nanopascal. And I'm going to highlight a few of these. This one is a paper that's out of PTB a few years ago. This is a primary gas pressure standard that's based on electrical measurements. In the figure, you can see there is a traditional pressure realization device, a piston gauge that I'm sure many of you have seen. And it's connected to another device that allows a researcher to combine theoretical values of helium polarizability with theoretical values of virial coefficients of helium. And of course, to remind you, virial coefficients are necessary when we expand the ideal gas law to the case of real gases with interacting particles, in other words, at higher pressures. And we include a measurement of a dielectric constant, and a change in capacitance gives us a change in pressure. So this is a primary realization of pressure at megapascal that does not rely on calibrated masses. We have another technology that operates around an atmosphere based on refractometry. There is an effort at NIST, which is my home institute, to develop this, as well as an effort in MPEER. This is a technique that takes a dual cavity device. One cavity is filled with the gas of interest, and the other cavity is maintained at a vacuum. And when a laser is introduced to this device, the laser that traverses the gas-filled cavity picks up a phase shift relative to the one that traverses the vacuum-filled cavity. And when the light is recombined, there's a beat frequency that is that transduces the pressure inside the cavity. And that is traceable again to helium calculations, in this case, again, the virial coefficients at higher pressures, as well as the polarizability. And that means that this is, again, a primary standard for helium, and it can be made in a deployable form factor. So this can be made into a device that you could bolt onto your chamber and get a primary measurement of pressure without needing traceability to a manometer or a piston gauge or any other pressure measuring device. A device that was spearheaded by, I believe, PTB and has been since developed into a commercial gauge produced by Inficon. This photograph is one that we purchased. This is our own Inficon gauge that we have bolted to a chamber in the vacuum lab at NIST. This is a standard ionization gauge, and what this is, it's just a well-engineered gauge that has a well-characterized electron path, and that gives you predictable sensitivity. And that means that it is reproducible over the pressure range of down to, I want to say, 10 to the minus 6 Pascal. And that makes it useful as a transfer standard in that range. And then finally, at the very lowest end of our scale, there's work to develop vacuum standards based on cold atom traps. And this is work that I've been involved in. The NIST prototype is shown in the photograph on the right. And the way this works is the following. It has long been known that the lifetime of a trapped cloud of cold atoms depends on the level of vacuum in the chamber. And all we do is invert that relationship to turn it into a sensor of the vacuum. And that sensor is based on the lifetime of the trapped cold atom cloud. If you do this carefully and painstakingly, and you take very good care to make sure that all of your possible uncertainty components are minimized and included, this again is primary. And Our prototype is up and running, it works, and we've got a number of papers out. There's one under development at PTB, and the University of British Columbia in Vancouver has one as well. They've got a number of papers. I apologize, I don't have a photograph of that one, but if you want to look it up, the PI on that project is Kirk Madison. And again, that's out of the University of British Columbia. So to sum up all of those technology trends and challenges, the important thing to point out here is that for pressure, we can call a Pascal as a Newton per square meter, but it's also an energy density. It's also a joule per cubic meter. And in light of the redefinition of the SI in 2019, and all of these emerging techniques that allow us to realize the Pascal in a fundamentally primary way without reliance on successive chains of calibrations back to manometry, it might be useful to start to think about how our relationship to mass metrology should evolve. And at the moment, of course, there's still in the field, all of these techniques and technologies are new and we don't have them deployed. And it will be decades before people actually get rid of their manometers. People will never get rid of their piston gauges, and we're not going to divorce ourselves from mass anytime soon. But the day might come, and it might be time to start thinking about what that will look like when it does come. So with that, I will wrap up, and thank you very much for your attention.
Okay, then I have to present the working group on hardness. An overview, the chair is me in this working group. It's my name correctly, Febo Menelao. I'm from PTB in Germany. Our vice chair is Dr. Korishiro Hattori from NMIJ in Japan. We have 18 national metrology institutes, which are members in our working group. It's the CNAM from Mexico, in Metro Brazil, CRIS Korea, INRIM Italy, NIM Thailand, UME Turkey, SMU from Slovakia, FNIF from Russia, GUM Poland, FNIM also from Russia, CAPES from Kenya, LNE France, NMI from China, NIST USA, ISA South Africa, NPL United Kingdom, RISE Sweden, and VSL in Netherlands. The working group on hardness is established by the CCM in March 1998 as an ad hoc working group. So long was an ad hoc working group from 1998 to 1999 was Dr. Kozo Lyutka from NILM in Japan, the chair. After this, it changed from an ad hoc working group to a standard working group. And Alessandro Giammac from INRIM going to chair this. I think it was not a comment. Was going to chair in this standard working group. And from 2014 to 2022 to the retirement of Sam Lowe, he was chair in this range. He was from NIST USA, and up to his retirement, I'm the chair of the working group since beginning of 2023. We have meetings nearly once a year from the beginning on. So we have mostly the meetings in September around, so that we are once a year a meeting doing the ISO meetings where we are coming together. Our terms of reference, the working group advised that the CCM on matters relating to the hardness, to improve harmonizing of preliminary standards by developing new primary definitions, or organize pilot studies to conduct key comparisons for supporting the CLC MER, to review the results to complete key and supplementary comparison and plan a support of the new comparisons, to facilitate to submission and review of the CMCs by establishing technical review criteria and service categories and providing guidance on coordinating the review process, to support activities in the regional members organizations, to produce working documents for the evaluation of unsanity, the main good links to interface with the Hardness community, for example, the IMICO TC5, to provide formal liaison among organizations involved in the standardizations. That means the ISO community, also the ACM community. Mostly the audience are not so familiar with the hardness, what it is saying the hardness in short explaining by the definition. Hardness is the resistance that one body offers to the penetration of another harder body. That's meaning we have not really a nature constant by our, or for our measurements, look like the mass and so on. That's make our measurement a little bit complicated. The description of the proceeding of the definitions is the procedure itself for the unit. It is not possible to calculate values between scales. Between scales, you can only convert it. So we have many scales to in this working group. So we have scales look like Brine, Vickers, Rockwell. It look like the standard or a little bit older measurements. Noob, Leap, Shaw for metal, Shaw for plastic. EHRD is called International Rubber Hardness Degree. Let's say it's the name is for rubber. Instrumented indentation tests, it's look like for many material which is possible to measure with it. UCI is an ultrasonic compact impedance measurements. The Poldy hammer, also through indenter viewing scales what we have, and many more which I cannot say it here. It's the list is a little bit longer, but not all of the scales are then is not involved in our working groups. Also, we measured not only the hardness itself, also the indenters which penetrate the material. Key comparisons, here's only a list which we can find on the BIPM website on the CMC. It's only shown you that the numbers or possibility of huge key comparison or comparison what we have. The problem itself is we does not make the complete group inside of the comparison, because therefore we have mostly regional comparisons which are not registered by BIPM. So why we have mostly regional comparison, we have shown here kinds of reference blocks. You can see we have limited size of the block, and if we are make indents on a block, look like here on a small indent, this area is lost by the measurements. There's a problem by hardness measurements. For example, a force transducer, you can measure it thousands times and more if you does not destroy it. Here we can only measure so long we have space on this block, and we have all of the indents, and you can see here around the indents the material is deformed after we make an indent. That's meaning the limitation is of number is limited. So I want to say. So you can see that not all of the institute can measure it on one block. That's the reason why we make only a comparison between some institutes, not all of them. By pilot studies, the new the indenter measurements are new in our program, so that we have made a pilot study by the geometry measurement of an Rockwell diamond indenter. A second pilot study is makes the Leb hardness comparison. Is also new in our group. It's also under construction. It's not finished because this is not possible to see in the website. It's coming later. And the third what we have is to find the pilot study 3 by Brina's hardness comparison. There we find new signs by the last comparison. That's meaning that the measurement optics are very important by the comparison or by measurement the hardness, and this was very was in a huge range what we are made with very different objectives, and therefore we have to harmonize the microscopes what we have used. And so we changed from the normally key comparison to a pilot study because this was not so, the comparison was not so made ideal because the different microscopes make very different results. Therefore, the definition at this time, the definition of the Rockwell scales. Come to the next slide. I showed you also the better definition of a diamond indenters look like Rockwell, Vickers, and Knoop, because the indenters are made in diamond, and the diamond constructor does not like the form which is shown you, the Rockwell, Vickers, and Knoop scale. For example, the Rockwell is in cone with an opening angle of 120 degrees and a ball-shaped part on a tip. And this is the diamond structure does not like to come to this form. The polishing and producing is not so easy to make. So that we need to measure the indenter itself. So that we have an influence after it about the manufacturing of the indenters after it, we hope. Here we have the definitions of our scales, what is finished, and you can find the guidance documents on the website. For example, the Rockwell scales, I said, here's these pictures show you the procedure of the Rockwell scales. We have a preload phase, then we go to the main load, and after it, special time, we're going back to the preload. And here you can see the indenter, what's going deep in the material, and both definition points give your value about the hardness. But the standard or ISO and ISTM standard give us a huge range of this procedure. So we get and we have to come minimum by the National Meteorology Institutes have to come closer together. So we define all of these times and speeds what we need to a table, which is showing here. And so we are the same procedure in all NMIs. And the Rockwell have approximately 30 subscales, look like also the other scales, Vickers, Brinell, Knoop have also many subscales, So we have many to definition all of these scales. The other guides, what we have is the guides on the estimation on hardness, uncertainty and hardness, as an Euromed guide, and also it is also find although the producing the uncertainty measurement for all of the NMIs. This will be described in easy procedure for the uncertainty measurement and hardness. The liaison and stakeholders, what we have is an ISO committee, is the TC 164, and the material testing of metals. There's a subcommittee 3 for hardness. Also, stakeholders is manufacturers of hardness reference blocks, manufacturers of hardness testing machines, calibration and testing laboratories in hardness, the complete steel industry, the car, aircraft, space travel industries. All of you knows that the car changed to an electrical one, and the battery is having very high weight. That's meaning to make the car more efficient. The other materials have to going to a limit, that the steels going thinner and so on, but the car must be also get by a crash, must also must be safe for the passengers. So that's meaning the car must be lighter, but must also be safe. On other liaison we have with the IMECO TC, with the IMECO, there's the Technical Committee 5 for hardness measurements. And I have to make a small commercial. That's meaning in this year, 2024, the IMECO going to a World Congress. This World Congress is organized by PDB, also my institute. And you can find some information by the website imeco2024.org. And it is possible to go there and find from all of our working groups what you heard, the newest measurement procedure, the newest result about the measurements in from all of the working groups. Yeah, our technical trends and challenges is to characterize new materials with layers with the same properties than the actual materials, but lighter, stiffer, or firmer, look like the car industry, I have said, and to measure the thinner or the layers on site is an other materials. It's not a based material, so that have other properties. So we have also the measurements of these very thin layers of the of metals. Also, the additive manufacturing is a new procedure to create some things. And there, the material going also thinner for the producing, and the time and type of manufacturer is very important there. The melting process by the different layer sizes are very important, so you get another material when you the layer have many time to cooling down, or you make the layers fast on site, then you get 2 times of different materials. This is also give a different answer about the material test, and this one of the hardest measurements. And also what we need in the next time is a better definition of the hardness testing. For example, how is the definition of the edge by a Brinell, Vickers, and loop indent? I should prefer the an indent, and there is not define where is really begin and ending the indent itself. It's only the set measured the edges of the indents, but where the indents will begin and end is not said in the standard. There's going to a new Euromed project called TraceInt BVK -H to follow this program. And the definition of manufacturing of hardness diamond indenters, I said that the crystal structure is not easily to manufacture the indenter imperfect. So that's meaning that different indenters give us different hardness values, and this is to harmonize that is also a challenge what we have to do in the next time. This is my information, and I hope you can follow it, and I'm free for questions.